Hey guys, we're starting off in the computer today. We're going to be doing a new concept called emission spectra, which will connect in with tomorrow's lesson, tying back to the Big Bang, of course. I hope you were able to do that recap of the Big Bang theory itself and cosmic microwave background radiation all right. I hope these videos are working out for you. Try to switch it up so it's not always this as we move forward, but certainly know that if you are stuck on a concept, you can look up any number of YouTube videos or articles on the internet. You're not confined to just using these videos. And of course, I'm open to any feedback you have to share. All right, so at that, we'll get underway. A couple learning objectives for you today. I want you to be able to describe what emission spectra are. I want you to be able to explain how they occur in atoms. And then lastly is just a general note. If you could please start actually submitting assignments in Schoology, hitting the submit button, that would help me track them easier. I know that's counter to what I've said in the past, but different times call for different measures. So I would appreciate it if you'd start submitting assignments. Thank you. All right, so we're going to take a little break from stars and galaxies just for today. We'll come back to them tomorrow, and we're actually going to go inside the atom. And so let's begin by just defining what an element is. You've probably heard this before, but elements are the simplest forms of matter that can exist on their own. And atoms are those microscopic pieces, particles, that make up elements. And each atom has a different number of protons, neutrons, and electrons, the subatomic particles, depending on what element it is. And we can see some examples of elements over here. We've got hydrogen, which has only one proton and one electron, versus helium, which has two electrons, two protons, two neutrons, and then carbon has 6 of everything. So atoms differ in size because they differ in the number of subatomic particles. An important and fun fact is that hydrogen is by far the most abundant element in the universe. About 75% of all the matter in the universe is hydrogen. So when we look at a distant star or galaxy, we're looking at primarily big collections of hydrogen. That'll come back around in just a little bit. And right now, for this particular story, the story of emission spectra, we're really concerned about electrons and what electrons are doing. Electrons are the subatomic particles that orbit outside the nucleus, outside the protons and neutrons of an element. So the electrons are kind of in this cloud outside of the center of the atom. And that cloud is where we'll be spending our time today. So when it comes to electrons, we have these things called energy levels. And energy levels are a set distance from the nucleus that electrons can orbit at. So here we see 4 different energy levels, K, L, M, and N. An electron can exist at any one of those rings. The important thing is that it can't exist in between them. So an electron can move from one energy level to another. An electron could, say, jump from K to L, but it cannot orbit in between them. There is no like half K, half L. You're at one of these 4 rings and no other possible positions. The farther the electron is from the nucleus, the more energy we say that it has. That's why they're called energy levels. Even though they're distances, they're also correlated to the amount of energy of the electron. And moving away from the nucleus is increasing energy. The way I would think about this is it's like taking an object and lifting it up farther from the center of the Earth. As you do that, you're storing more gravitational energy in that object. Here, as you take the electron and try to pull it away from the positive nucleus, you're taking that negative charge and moving it away. That's increasing the amount of electrical potential energy it has. So we have a couple different states we like to talk about when it comes to electrons orbiting at different levels. The ground state is the lowest possible energy level for an electron. Again, this corresponds nicely to the gravity metaphor. If an object's on the ground, it has no gravitational energy. It's at its lowest possible gravitational energy. If an electron is as close to the nucleus as it can be, we say it's at its ground state. A different state is an excited state, and that would be when the electron has moved up to a higher energy level than it would normally occupy. When the electron gains energy, we say it becomes excited. So you might wonder then, how do electrons move from ground state to excited state? If an electron gains some energy, and that energy could come from light or heat, when an element is heated, the electrons in those atoms gain energy, and they capture that energy and move from ground state to an excited state. That's kind of half the story here. But then, when an electron falls from the excited state back to the ground state, that energy has to go somewhere, and it's released as a photon, as a particle of light. So that's what this particular image is trying to show, is the electron up here in energy level 2 is falling back down to energy level 1, and when it falls, the energy is released as a particle of light. So this brings us to what emission spectra are. First of all, emission means to give off, to emit, and spectra is talking about the electromagnetic spectrum. So this is talking about the types of light that are given off on the electromagnetic spectrum as electrons are heated and kicked up to excited levels and then fall back down to the ground state and give off light. So emission spectra are the unique bands of color given off by an element as electrons fall between the element's energy levels. So if I were to take any one of these elements and heat it up, and then I see the electrons falling back down to different energy levels, I'm getting these unique bands of color. So for beryllium, for example, you've got purple, the dark blue, the light blue, and the green. That would be beryllium's emission spectra. The emission spectrum of an element is like the element's fingerprint. Each element has a different emission spectra because each element has different and unique energy levels. Those rings don't fall at the same distance for all the same elements. They fall at different distances for different elements, and so therefore you get different bands of color. And like we use fingerprints in forensics to identify people, we can use the emission spectra of elements to identify the element. So in this case, say I have this unknown emission spectra up here. It's got kind of these 4 colors of blue and these 3 colors of red. I can check it against my known fingerprints and see which one it matches up with. So it's not beryllium, it's not copper, it's not manganese, it's strontium. Strontium has those same 4 blue and 3 red in the same location. The farther the distance from excited state to ground state is, the higher the energy of the light emitted. And what that means is a higher energy photon is going to have a shorter wavelength. It's going to be more frequent. And for visible light, that means it'll be more on the blue or purple end of the spectrum. We'll see an example of that in just a minute. And then lastly, and important, is if you want to actually get these individual bands of color, what you're going to have to do is take the light given off by an element, and you need to separate it by its wavelength. And the 2 ways that we can separate light by its wavelength is either diffraction or refraction. So often what we do in astronomy is we have a telescope, we shine it at a distant star or galaxy, and then we put a diffraction grating, the little pieces of rainbow paper that we used in the classroom, we put that on the other end of the telescope, and what comes out are unique bands of color. And those unique bands of color let us identify the elements in those stars or galaxies and add to the story of the Big Bang, which we'll get to tomorrow. Here is an example of what you might see coming out of the other side of a telescope. This is an actual emission spectra of a distant galaxy. And what we see are these, well, what we see, first of all, is on the y-axis is a really fancy way of saying brightness of light. And on the x-axis, we're graphing the wavelength. So you could think of this like color. And what we see are these really sharp peaks coming out of this curve. So the curve itself is just saying that the galaxy is giving off some light at all different colors. But we see really tall peaks at certain unique points. And these four specific peaks that are pointed at with these red arrows correspond to the emission lines of hydrogen. So we know there's hydrogen in that galaxy because there are these four specific peaks. As you go through the assignment today, you'll have a set of basic proficient questions that follow pretty much right from things I've already said or words that are on the slides. So those should be pretty straightforward. And then your proficient section is to kind of put it together in a paragraph, explaining what happens inside the atom to create these unique bands of color. And I'm going to go through that. I'm going to try to talk my way through that paragraph right now, and then you can try to summarize it and put it in your own words. So we said hydrogen has four unique visible light colors that come off from it. We can see that here on this. Here's a zoom in of the hydrogen atom itself. Just to set the story real quick, set the stage. The red dot is the nucleus. The yellow dots are electrons, and the black rings are energy levels. And in this case, the ground state for these electrons is n equals 2, the second energy level. And the excited states, the states that these electrons can travel to, are 3, 4, 5, and 6. Now, if you have a big cluster of hydrogen and you add energy to it, say it's hot because the star itself is burning, these electrons are constantly being kicked up to one of these four energy levels, thousands of times, trillions of times, every second, and then falling back to the n equals 2 energy level, again, trillions of times every second. And that is creating four unique colors of light. This one here, to go from n equals 3 to n equals 2, is red light because that distance is very small, and red light is the long wavelength, low frequency side of the spectrum. To go from n equals 4 to n equals 2 is a higher energy photon because the electron fell a farther distance. We're starting to move towards that purple side of the spectrum. And then we go n equals 5 to n equals 2, it becomes even more purpler. And then the highest energy photon given off by hydrogen is when an electron falls from n equals 6 to n equals 2. So it's important to know that there are trillions of these photons being generated when you have a cluster of hydrogen burning. But those photons can only be on one of these four colors of light because those are the four specific transitions that those electrons can make. It's not like it could go from 3.5 to 2 because 3.5 just isn't an energy level. And if we were to look at a different atom, say helium, it would have its rings at different positions, and therefore when it had its electrons falling from excited to ground state, it would give off its own unique bands of color. So this is very specific to hydrogen. You got the red, the light blue, and the two purples, which is probably the most important emission spectra in astronomy because hydrogen is most of the universe. When we go back, and we'll just take note of a couple of these numbers, the red line is at 656 nanometers. The farthest purple is at 410. We go back to the emission spectra of the galaxy. To convert that nanometers into angstroms, we just multiply by 10. So the 656 nanometers is 6,560 angstroms, and that's about where this peak seems to be falling. The 410 is actually 4,100 angstroms, and that's about where this peak is falling. The scientists again can say, because we see these four bands of color, therefore we know hydrogen is in that galaxy. To summarize this story real quick with a student's presentation from last year, they built a model to capture kind of what's happening in the atom in four steps. So you've got your electrons at the ground state. They get some energy from heat and they move up to an excited state, and then they lose that energy and fall back down to the ground state. And when they do that, they give off those four unique bands of color. And that happens over and over in the atom, trillions of times a second, but only those four bands of light can be given off because those are the only four possible transitions that the electrons can make. So I know that was a bunch of new information, a lot to soak in there. Please give me feedback on if this is working. I'm going to start going through your assignments tomorrow since the first one's technically due tomorrow. Again, let me know if it's working, if it's too much information, if it's not enough, or if you need to access it in some different form. Just stay in touch and we'll keep getting through this. Thanks, guys. I will see you again soon.